Hi everyone. Today we're going to continue talking about logistic regression, um, continuing with our discussion last time where we looked at a simple logistic regression where we have one predictor in our model and how we can use that to model a binary response, a categorical response with two levels. So today we're going to talk about some assumptions that are necessary for our model, how to assess if our model is fitting the data well based on these assumptions, and how to conduct formal inference using hypothesis testing and confidence intervals regarding coefficients for our model. So to recap, we've seen how we can model a quantitative or continuous response using a binary outcome. Okay, so but for logistic regression, we're interested in the probability or the chance of an event occurring, where an event can be something that's considered a success or failure. It's a binary in that it has two possible outcomes. So that's when logistic regression is applicable. And specifically, how R or other software treats this logistic regression problem is that we have a response variable that's coded as being 1 for the event occurring or 0 for it not occurring. So for example, we could see how we can model the chance of an email being spam or not, where we could say the email being spam corresponds to y being equal to 1, and the email not being spam corresponds to y being equal to 0. Okay. And we're going to be looking at simple logistic regression in this video, which is just the case when we're using a single predictor in our model. And this predictor x can be either quantitative or categorical. Okay. So for the logistic regression model itself, here is the assumed model that we're using. So we're modeling the log odds, where the odds is defined as pi over 1 minus pi, and pi is the probability of the event occurring. Okay, and we model that as a linear combination of our predictor variable x, where again we have beta sub 0, beta naught is the intercept term, and beta 1 is the regression coefficient for x1. Okay, and specifically what is commonly done with logistic regression is this log transformation is the log base e. I know sometimes in other areas they use log base 10, but for logistic regression, it's important that we're using the log base e here. Okay, and just to plot what this looks like, this implied model here is that if we plot the probability of success on the y-axis here, which is pi, and then the linear predictor, sometimes they call this the intercept plus the regression coefficient times x, we end up with this sort of S-shaped curve for the estimated probability or the probability of success here. And we can see, as we mentioned last time in a previous video, that this S curve is constrained between 0 and 1. So there's sort of these asymptotes, these horizontal asymptotes here at 1, where this S curve will keep getting closer and closer as the linear predictor gets bigger. It'll get closer and closer to 1, and then as the linear predictor gets more negative, it gets closer and closer to an estimated probability of 0. Okay, and this is sometimes called the inverse logit function. And that's because this log odds is called the logit function of pi. So to undo that logit function to solve for pi, we use the inverse logit function. Okay. So just like with multiple linear regression, there's some necessary assumptions that this logistic model relies on. So there's not as many because we don't make assumptions about the errors like we did before, but we're still needing independence of the observations. And we also want a random sample. So we can't have something that's deterministic. For example, if we wanted to say, if we were modeling the probability that someone's, for example, someone's mascot for their school is Goldie the Gopher, and we're using whether they go to Minnesota or Augsburg as the predictor, that's sort of a deterministic thing, because if you go to Minnesota, your mascot has to be Goldie the Gopher. And if you go to Augsburg, your mascot is not going to be Goldie the Gopher no matter what. So that's a sort of predetermined thing. It's not really random. So that wouldn't be a setting in which we model using a probabilistic model like logistic regression. So that's just a little bit of a side note, not usually an issue we need to think about, but more importantly is this linearity assumption. So even though we have this S-shaped curve, there's still an implicit linearity assumption that this logistic regression model relies on here. So specifically, if we looked at the logistic regression model itself, this is assuming that X is linearly related to the log odds. Okay, so it's not the same as multiple linear regression where just X was linearly related to Y. It's now linearly related to log odds, where pi is the probability of success. So this seems like it'll be a little bit more difficult to check in practice, but there's still ways that we can check this using what's called empirical Logit plots. Okay, and these are helpful to check. So this isn't necessary to do if our predictor is a binary predictor. So if it just has two levels, this assumption won't really be violated ever, because it's just not possible to have this nonlinearity when we'll just have essentially two blocks of points because of the two levels of the predictor variable. This linearity won't be violated ever for that. But for a continuous predictor, this can help inform us of potential transformations that are needed, or if just some weird patterns in the data are going on. And we'll look at an example where that's the case. So if we recall this data set on Titanic passengers, we have our outcome variable being whether or not a passenger survived. Okay, so survived is yes, is the success, and so that is y equals 1, and y equals 0 is the passenger did not survive. And we can consider modeling the probability of survival using the passenger's age in years. Okay. So using the GLM function here for a generalized linear model, we can fit a logistic model by specifying family equals binomial, and then get the regression model output here. Okay, and from here we see that we had a lot of missing values. There was a lot of missing ages for the passengers, but we still have 756 passengers who had the full data here. So looking at this model fit, we see that our estimated coefficient is pretty close to 0, and the p-value is actually still pretty small, but above 0.05. So using a 5% significance level, we do not have evidence that age is related to the probability of survival for the Titanic passengers. Okay, and I'll write out an interpretation of the regression coefficient here, though, just for demonstration. So, since beta hat equals 0.009 for every 1 year older a passenger on the Titanic was, their estimated odds of survival multiplied by, okay, and then we need to calculate calculate this value. By exponentiating it, so we set e to that regression coefficient to get it off of the log scale, because otherwise the increase is on the log scale. So since beta hat equals minus 0.009, for every 1 year older a passenger on the Titanic was, their estimated odds of survival multiplied by 0.991. So they decrease by about 1% odds of survival for every 1 year older a passenger was. Okay, so that's how we interpretation of the regression coefficient. Okay, and we can actually interpret the estimated intercept as well. Since the estimated intercept equals that, this is representing the estimated log odds of survival for a newborn, a passenger with an age of 0. So but we don't want this on the log scale, so we're going to say the estimated odds of survival for a newborn on the Titanic is about, and then again we have to calculate what this e to this value is. Okay. Okay, so that was the estimated odds of survival. All right, and if we remember, odds is slightly different than the probability of the event occurring. Although they tell a similar story in that a higher odds of the event occurring corresponds to a higher probability of an event occurring. Okay. So anyway, this is how you interpret the intercept and estimated slope for this logistic regression model. Okay. So plotting this empirical logit plot, we're now going to check this linearity assumption of the log odds being linearly related to our predictor variable age here. So using this function Emp Logit Plot 1 for empirical logit plot from the stat2 data package, we can plot this. And what's going on here is we have to bin the groups, the data into different groups in order to plot this empirical logit plot, because we actually need estimated probabilities. If we look at the logistic regression equation here, what we're checking is we want to plot this value on the y-axis, the log odds, and then we're plotting this linear predictor with our estimated coefficients plugged in on the x-axis. And the idea is these should be linearly related. That's what our models is relying on. Now, we don't actually observe pi's in our data set. We don't observe probabilities of an event occurring. We just observe discrete outcomes. So a passenger surviving or not, which is either 1 or 0. So we can't actually plot the raw values in that way. We can't just use 0s or 1s for the pi's, because if we plug in 1s or 0s here, we would end up with log of 0 or log of an undefined value. Okay. And so these would be undefined if we plugged in zeros and ones. But what we can do is we bin, so for example, if our predictor is age, we will just bin or group multiple passengers in different age categories. So for example, in this function, I specified 5 groups or 5 bins to group passengers by age. So we separate the range of ages into 5 different groups of ages. So we have like a lowest fifth of the passengers in terms of age and like a highest fifth of the passengers in terms of age. And then we look at the proportion within each of those 5 groups who survived or not. And so that's how we can get an actual pie from our data. So this will vary slightly depending on the number of groups that you pick, but by specifying 5 groups, we'll get 5 data points for this empirical logit plot here. And the idea is this should be a linear relationship. So here what we see is that the log odds for this data set by specifying 5 groups is not looking very linear. In fact, we see this very troublesome U shape. So this is not good. What this is indicating is that passengers, very young passengers, had a higher chance of survival, and then very old passengers also had a higher chance of survival. But then in between, like passengers around 30 years old, it looks like had the lowest chance of survival. So this makes it difficult for our logistic regression model because it sort of wants this monotonic relationship. It wants it that as age increases, the probability of survival needs to be changing in a consistent way. But that's not the case here. We have this U shape. And this commonly occurs in some real world settings, just like this. I mean, this is a real world data set. For example, I was just looking at another example, reading an article where like consumption of the amount of vitamin D that people were consuming in a certain longitudinal study had this sort of U shape with the probability of adverse outcomes, where if you had far too little vitamin D, the probability of a bad outcome was higher. And if you took a higher amount that was not too high, the chance of bad outcomes decreased. But then if you took way too much vitamin D, the probability of adverse outcomes increased again. So it's sort of a U shape again. So this can sort of just make it difficult to model data with logistic regression. So it's good to plot this to see if you have these potential problems in your data set. So what can you do if this happens? Well, what you could do, although you have to be careful with not sort of arbitrarily making predictors that just fit your data well, you could have a variable, make new variables that say like, is someone less than 20 years old? So that's going to be a variable, yes or no, a binary variable. You could have someone between 20 and 40 years old. That could be a second variable. And then is someone older than 40 years old? That could be a third variable. And then ideally what you'd see is like within that, each of those variables, then it would have a linear relationship with the log odds. That's one possible solution, although it might just be this not a good predictor to include in your model as well. So anyway, with this main takeaway here from the empirical logit plot, this linearity assumption is questionable for the predictor age. Okay, so now we can see why maybe that p-value wasn't very small. Has to do with this U shape occurring in the data. So what about checking that randomness assumption that we talked about? Well, that's a little bit more difficult. So we'll consider some examples from the textbook that they look at for when this randomness assumption is violated or not. Okay. So this first example, they call it male chauvinist pigs of yesteryear. So I didn't know what chauvinist meant. I had to look it up, to be honest. I knew it wasn't a good thing, but apparently a chauvinist is a person who thinks they are they irrationally think they are better than another group of people based on the group that they belong to. So male chauvinist pigs are men who think they're better than women irrationally just because they're men. So this example talks about how during the 70s, women were entering the workforce at higher numbers than they ever had before in the United States. And one survey, so I guess this was a real thing, asked randomly sampled men and asked them if they agreed or not that women should stay in the home and let the men run the country. So that's a little embarrassing. So we can think about this as a logistic regression problem where we model the probability of men agreeing with that statement and use their education level as a predictor. Okay. So in this data example, is a logistic regression model appropriate here? Is this a random sample where we have a binary outcome? So yes, here, because they had a random sample of men, we can apply logistic regression and model this probability. Okay. And for those who are not familiar, this is Rosie the Riveter, who is an icon for women in the workforce during that time. Okay. All right. So a second example. In this case, logistic regression was appropriate. So now let's think about another example. So this one's called bodies of water. So we suppose we have some doctors who want to model the proportion, so proportions are between 0 and 1, of the human body that is water. And they collect different variables such as the age, the sex, the weight, and height of different patients. And their statistician tells them, hey, that's a proportion, use logistic regression. But is that appropriate here in this setting? Maybe you can tell based on my intonation already. No, this is not a setting where we would use logistic regression. It's understandable that you might think, oh, it's a proportion that's between 0 and 1. That's like a probability, so we use logistic regression. But the problem is, for logistic regression, we actually need a discrete outcome. We need an outcome that can be coded as zeros or ones. It has to be that way. Okay, so we can't have this case where we have the proportion of each person's body that's water. So if you think about this actual data, we'd have the case that maybe somebody's body, I'm not sure how much water makes up people's bodies, but let's say it's like 90%. So if we measured somebody's body as being 0.91, that's the proportion of their body that's water. That's not 0 or 1. So for each person, we'd get a measurement like that, but we need it to be zeros or ones to model with logistic regression. So actually, we could use just regular linear regression in this case, or a different type of model that can handle this better. Okay, so logistic regression was not appropriate in this case because although we might have a random sample, the response needs to be discrete or binary. Okay. What's more commonly violated when people use logistic regression is independent observations. So this can be violated in a few different ways. One common way this is not met is when points have sort of a temporal or time aspect to them. So values closer in time might be more related. So for example, let's say we wanted to predict the chance of a company's stock increasing or not on a particular day. Okay, and then we have values of that measured across time, every day, daily increases or decreases for a company. Okay, those values are not going to be, those days are not independent because we have days closer in time are going to be more related. So for example, maybe the economy was doing really well in April, then days in April are more likely to have increases in the stock's value. But if the economy is doing worse, say in February, again, it's more likely that those days which are closer together might have decreases in the stock's value. So those day-to-day observations are not independent because they are potentially more related the closer they are in time. Another example where this might be violated is like a spatial aspect in the data. So we talked about time, the temporal aspect of potential dependence there, but there's also spatial relationships that can be happening. So for example, if farmers wanted to model if a new pesticide prevents infestations in their fields, maybe they applied this pesticide to many different fields, treating them each as an observation. But adjacent fields, so fields that are touching, are going to be more related than fields that are further apart. So this creates some sort of dependencies in the data, violating this independence assumption that's necessary for logistic regression inference. Okay. But it's important to note, even if these assumptions of a random sample and independence are violated, we can certainly still fit our data, fit our model to our data. There's nothing that's going to stop us from doing that. It just means that the confidence intervals that we get, these standard errors and hypothesis tests for statistical inference, are no longer valid. These things are based on the amount of uncertainty that we have in our estimates in our data. And the idea is that the main sort of intuitive understanding for why this is a problem is that if we have dependencies in our data, there's sort of redundancy. Okay. For example, like with the stock increase or not, we may have measured values on 100 days, but if they're very similar to each other for days that are closer in time, our like effective sample size is sort of smaller. If days in the same week are always very similar to each other, then 7 days is really kind of only like one data point, for example. So we have sort of a smaller amount of information than it may seem. And so with more dependencies in the data, these hypothesis tests, confidence intervals will be more confident than they should be. They'll be too confident. Okay, so that's where the issues come from. But in terms of obtaining estimates, predicted values, we can still just fit these models if we want to. So assuming independent sample is met and the linear relationship based on the empirical logit plots is met, we can do statistical inference. We can do hypothesis tests. So one common hypothesis test we'll want to do is testing if the regression coefficients are 0 or not. So just like with linear regression, we test formally the null hypothesis that the regression coefficient is 0 compared to the alternative hypothesis that it's non-zero. Okay. And for logistic regression, we'll use what's called a Wald statistic. So this is named after a guy whose last name was Wald. And this is also called a z-test statistic. And this is calculated as the regression coefficient divided by its corresponding estimated standard error. Okay. And using this z-test statistic, we can get a p-value based on a standard normal distribution. So software will help us do this. Okay. Getting the regression output from R for our logistic model that we fit earlier, or this is a model where we're using actually the sex of the passenger to predict the probability of survival now. Okay. And here we see that the p-value is about 0. So the sex of the passenger seems very important in terms of whether a passenger survived or not. So we can interpret this regression coefficient here. Okay, so since so in this case, I guess first it would be important to mention or how we define this predictor. So sex male equals 1 for male passengers and 0 for female passengers. Okay, and so based on that, from the regression output, the odds of a male passenger surviving on the Titanic were we exponentiate the value in order to interpret it. We'll use R again to calculate what that is. So the odds of a male passenger surviving on the Titanic were about 0.1 times the odds of a female surviving. So that's the odds. If we want to get the probability, this is a little bit more complicated, but what we can do, so the odds is equal to, if we recall, odds equals, if P is the probability, P over 1 minus P, okay? And so that actually tells us that P, if we solve for it, is equal to E to the odds over exponentiated odds plus 1 over E to the exponentiated odds. Go through the algebra to solve this. This is what you'll find. So, okay. So if we look at that in R, all right, where we substitute the estimated odds here. All right. So this gives us the, oops. Sorry, I'm typing a lot here. So the odds of a male passenger surviving on the Titanic were 0.1 times the odds of a female surviving. Okay. So if we wanted the probabilities, the ratio of the probabilities of survival, okay, what we need to do is think about, it's easiest to think about what's the probability of survival for a female, and then what's the probability of survival for a male. So okay, so let's see. Probability of survival given that someone was a female equals times 3, okay, and then the probability of survival given male equals, okay, then the ratio of those two things is going to end up simplifying down to, oh, I'm sorry, that's the odds. Yeah, that was my, oops. That was my mistake there. Okay. These are the odds of survival. Yes. All right. And then bear with me here, sorry. So this is the odds ratio for survival, males versus females, okay? And then But if we wanted the probability of survival, without losing this interpretation that I gave up here, there's a lot of stuff to fit on this slide, but I'll move this other interpretation up here. Okay. All right, and then down here, so we have calculation of the odds. All right, and then also calculate the okay, kind of running out of room on this slide, I guess, but I guess we won't worry about the probability of survival here right now, but this is how we'd get the odds ratio, okay, which we found was about 0.100. So that's how that makes sense. We get the odds of survival given female, odds of survival given male, and then if you take the ratio of those two, it simplifies down to just the exponentiated coefficient estimate. And that works out because this sex male predictor is binary. It has two levels, so this is not coincidence that it just ends up being the exponentiated coefficient. That's how that works out for binary predictors like that. Okay. And if we want the probability of a male surviving or the probability of a female surviving, you just have to use the inverse Logit function. So for example, I guess it might be helpful if I just show probability of survival given male. Okay, so that's going to be equal to the all right, e to the odds over 1 plus e to the odds. Okay, and so here we saw that the odds of survival for a male was this value. Okay. So then we just do that value over 1 plus that value. Okay. That's the probability of survival for a male here. That's how we solve for that. These calculations are a little bit tedious for logistic regression. We have to be careful. I think it's easiest to sort of break it up into pieces like I did here, where we get the odds of survival given female. So sort of for different outcomes one at a time. And then it makes it a little bit more clear what we're doing here. So anyway, these are things we can determine from the regression output here. For example, if we were asked, what's the probability of survival given a female, we could calculate it in a similar way using the odds up here. Okay. So we can also, those were just sort of estimates for single values, probability or odds of survival. We can also get confidence intervals. So for example, we can get a confidence interval for this slope, where the exponentiated slope represents the odds ratio here. We can get a confidence interval for the slope using a similar formula as we've seen previously, where we have point estimate plus or minus our confidence interval multiplier, which is now a z star instead of a t star like we've seen previously, times the estimated standard error. Okay. Or a convenient way using R is just to, in the summary function from the JTools package, we can also just specify conf int equals true. We want a confidence interval and we want the width for we want the confidence level to be 95%. So we can specify it in this way. And then we get a 95% confidence interval for the slope here. And so let's say we wanted a 95% confidence interval for the odds ratio, because again, this is on the log scale. So we wanted a 95% CI for the odds ratio. Okay. We would first exponentiate the bounds of the confidence interval. So minus 2.566. And since that's on the log scale, that's why we're exponentiating it. That equals that, and that was our lower bound here, and then minus 2.037. Okay. And using R. All right. Okay, since the exponentiated lower bounds are given by that and that, we say we are 95% confident that the odds of survival So we interpret this a confidence interval for the odds ratio. We interpret it as saying we are 95% confident that the odds of survival for male passengers was between 0.07 and 0.13 times that of female passengers. That's a confidence interval for the odds ratio here that we can get from this output. So again, a little bit tedious because we have to be careful about we need to exponentiate the estimates and then think about which group's comparing to which in terms of survival. And then we have to make sure we're talking about the odds of survival, which is not the same as the probability of survival. Okay. So a lot more stuff to keep track of than in just regular regression, but with repetition, with more practice, hopefully we'll get more comfortable with this and it will become more natural. But definitely good to practice these interpretations yourself and practice understanding what the output is giving us. Okay, and then sort of like I just obtained here manually the exponentiated estimates, you can actually have R sort of do that for you if you do this exp equals true argument in the JTools package. Then it'll give you these values. So 0.077, 0.13, like I just calculated up here. R will just give you those, and then you can save yourself a bit of work if you want to do it that way. Although it's good to know, to understand how you can get it from the unexponentiated output as well. Because sometimes in papers and stuff, it's reported in this way rather than exponentiated. So sort of moving on from interpreting the regression output that we get for this logistic model, we can also look at how we can assess how well our model's fitting the data. So for linear regression before, we saw how you can just use the R squared or adjusted R squared to see how well our model is explaining the data. Okay, but for logistic regression, we don't have an R squared anymore. We have a binary response, so we don't calculate the R squared like we did previously. But what we do look at is we can look at the likelihood of the data, which we denote with capital L. And so this can sort of be thought of as the probability of the data given our model estimates, or the probability of our model estimates being true given our data. That's a sort of informal interpretation of it, but not technically correct. But so this likelihood or likelihood function is a function of the unknown parameters holding our data values fixed. So essentially what we're doing is we select estimates of our regression coefficients. So we denote those with hats. And these are selected to maximize this likelihood, this capital L value. Or equivalently, the betas, the regression coefficients are selected to minimize the -2 times the log likelihood. So log is a monotonic function. So minimizing the negative log is same as the maximizing the log likelihood, which is the same as maximizing the likelihood. So I know that was a lot there, but just thinking about it carefully again. So minimizing the negative of something is the same as maximizing the positive version of that same thing. So that's how that's working. And then since log is a monotonic function, maximizing the log of the likelihood is the same as maximizing the likelihood. And the reason we go about using this quantity rather than just the regular likelihood is that due to statistical theory, this simplifies actually a lot of the calculations when doing the calculus behind this, the derivatives and such for optimization. So there's reasons why this is used instead of just the likelihood, but you guys won't have to worry about that in this course. So anyway, so this quantity, -2 times the log likelihood, is called actually the deviance. So you'll sometimes see this term pop up when looking at generalized linear models, is the deviance of a model. Okay, so this is sort of analogous. This deviance is analogous to the residual sum of squares in linear regression. So to test if our overall model is statistically significant with a single predictor, what we can do is use a likelihood ratio test. Okay, so this is kind of similar to a nested F test from before. So what we do here, the test statistic, which we denote with G, is given by the deviance of a model that just has an intercept minus the deviance of our model with our predictor included. Okay, and they call the model with just an intercept a constant model because the predicted value is the same every time. Okay, and then we compare this difference in the deviances to a chi-squared distribution with 1 degree of freedom. So they call this symbol nu. Okay, and then from that we can get a p-value. So software will do that for us. But here, for example, the software gives it to us, this chi-squared 1. This is our test statistic. And it doesn't actually give us the p-value directly up here, but we can calculate it using R. So the p-value is actually, if you calculate it using R, is like 2.7 times 10 to the minus 74th. So that's like 0. And then 73 zeros and then 27. So it's really, really small, really, really close to 0. So certainly since the p-value is so small, so close to 0, here we have evidence that the likelihood of survival differed between men and women. So we have evidence that sex male here is an important predictor to include in our model. Okay. So note that not only can we just test the overall statistical significance of our model, oftentimes we'll want to compare two different logistic models as well to see which one's fitting the data better. So one way we can do that is using AIC and BIC, which we've seen previously. So these are just two metrics that compare the fit of models fit on the same data set. And in general, smaller AIC or BIC is better. We want to pick the model with the smallest AIC and BIC. These will typically give the same decision on which model is best, but not always. These do, in order to compare models that were fit, we do have to have the same exact data set used for each. And so I noticed here for like the Titanic data set, we have some missing values, but it was just in terms of the passenger's age. There were some ages missing. So when the logistic model was fit using age, it excluded the missing value observations. But when the logistic model was fit using the sex of the passenger, it kept everything in. It didn't have those missing value problems. So those were actually using different data sets. So to work around this, I just subsetted to a complete data set. So I removed rows with any missing values using this code and then compared the models that way. So otherwise, the comparison using AIC and BIC is not valid when there's not the same exact data used. Okay, so fitting these models, we're going to compare whether using age as a predictor or sex as a predictor is better if we're going to just use a one predictor model. So storing those fits, and then we can calculate the AIC and BIC using the AIC and BIC functions in R. Here we can see that the model using sex of the passenger as a predictor has a lower AIC and a lower BIC. So this AIC and BIC suggest that if we're going to use a one predictor model here, we should use the model with the sex of the passenger as a predictor, which is not too surprising based on the regression output that we saw earlier. So again, the main takeaway, we want to select the model with the smaller AIC and BIC. Okay. And I've mentioned before how AIC and BIC are one way to select a model. Personally, I feel like a better way is to look at cross-validation error. So without getting into the details of cross-validation again, we want to have the model that has the highest prediction accuracy cross-validation folds. So using this CVGLM function from the boot package in R, we can calculate the leave one out cross-validation error, average leave one out cross-validation accuracy for each of these fit models. Okay, and just as a quick reminder, this involves leaving one data point out, in this case, one passenger out, fitting a logistic model on the rest of the data, except for that one passenger, and then trying to predict whether that left out passenger survived or not. And then doing that, leaving out every single passenger one at a time and seeing what our accuracy is using age as a predictor or sex as a predictor in that process. And the idea is we want the model that most accurately predicts the survival of each left out passenger when we fit it, when we fit the data. And so doing that, we see that the age model actually didn't do so great. So it's close to a 50-50 chance of whether it predicts the survival of each passenger correctly or not when leaving them out. So age is not great here on its own. But using the sex of the passenger, we got about 78% of passenger survivals correct based on the leave one out cross-validation fold. So certainly this suggests the model using the sex of the passenger as a predictor is better than age. Okay, so that wraps it up for this video. And thanks, and we'll talk to you guys again soon.